Now there are several ways that we can approach getting the volume of this region. I will consider the length of a line that's parallel to the y-axis. Okay, the starting point of this line is a point on the x-axis, and the end point is a point on this curve. Now we have the equation of this curve. It's y equals 4 minus x squared. Okay, whereas y equals 4 minus x squared actually refers to the curved surface of this object, but you know, if we take cross sections parallel to the xy plane, all the curves formed are identical. The z values change, but we're not interested in the z value. We're just interested in the relation between y and x for points on these curves that are in the surface of this shape. Okay, anyway, the y value of this point is 0, and the y value of this point is given by the equation of the curve, which is 4 minus x squared. So to get the length of this line, we just integrate 1 times dy from y equals 0 to 4 minus x squared. Well, we know the answer is going to be 4 minus x squared. It's clear. But you know, when we're getting the volume, we are integrating 1 over the entire region. Okay, so this will be the innermost integral. Now, to get the area of the cross section, this horizontal cross section here, we have to imagine this line moving in the x direction. Well, we could have it moving in the positive x direction. It doesn't matter actually. This line will sweep out the cross-sectional area that we're after. So we have to integrate this quantity here with respect to x. We have to move entirely in the x direction. So that's how we can generate this particular cross-sectional area. So what are the limits of integration here? Well, we could start off here at 0 and go as far as x equals 2. So if we perform this double integral, we will have the cross-sectional area shown in blue here. Finally, we want to imagine this cross-section moving upwards, and it will sweep out the volume of the region that we're after. So we are moving entirely in the z direction, so we have to integrate it with respect to z. And we integrate from z equals 0 to z equals 6. So all points in this cross section have 0 for their z value, and so we imagine the cross section sweeping it out. Well, actually we will just be multiplying by 6. Okay, we'll just be multiplying all of this integral here by 6, because we can see that the horizontal cross section doesn't change. This shape here is a prism. So let's take the innermost integral. Integrate 1 with respect to y gives us y. The limits are 0 to 4 minus x squared, and that's going to give us 4 minus x squared. And we can see that clearly from the diagram. Distance from here to here is just the y value of this point, which is 4 minus x squared. Okay, so now we take the next integral. So this is straightforward as well. Integrate 4 with respect to x, get 4x, then we get minus a third x cubed, and our limits are from 0 to 2. If we work this out, we get 16 over 3, so that's the area of the cross section. So now we just have to integrate that, which is that cross section, which is a constant, by the way. Okay, we just got a number for this second integral. Integrate that from z equals 0 to 6 with respect to z. Well, that's just actually 6 times 16 over 3. So that's 16 over 3 times z from 0 to 6, which is of course 16 over 3 times 6. That gives us 32.